Welcome to Pre-Calculus. Today we will investigate function behavior around discontinuities, focusing on what y value the function approaches from the left and from the right. Let's take a look at 3 examples. Let's head over to our notes screen. Our first example is this piecewise function. So we've got 2 parts to our function based on kind of a partitioning of the x-axis. So our first function is this 1 over x minus 4, which is in effect when x is less than -4. Our second function is 2 to the power of x, so an exponential function, and that's when x is greater than or equal to -4. So our first task is to graph this function. Once I graph it, I can see where is the discontinuity, and then I can answer this left-hand and right-hand behavior of the function around the discontinuity. But let's begin by graphing. So I'm going to create a t-chart here. And I know that I need to focus on -4 since that's the cutoff between one function to the next function in the piecewise. So I'm going to go -4 and then back up to -5 and -6. I'm also going to include some of these other values. So let's go -3, -2, -1, 0, and 1, just to catch that other function, the 2 to the power of x. Now I'm going to modify the table slightly. Whenever you got a piecewise function, basically you have 2 functions paired up into one. So I'm going to put 3 total columns in that table. The middle column will be the output or the y value for this 1 over x minus 4. So I want to calculate those values. So again, I'm just going to input the x value, the number in for x in the equation. So first here is 1 over -6 minus 4. And that's going to be -4 and 1/6, which has the value of about -4.1 repeating 6. Next value is 1 over -5 minus 4. And that is the value of -4.2. 1 over 5 is 0.2. And then -4, which really, that's the cutoff number. And really for this 1 over x minus 4, the one in red, that's strictly less than -4. So at -4, what we'd say is it's undefined for this red function. It really belongs to the green 2 to the power of x. But we want to calculate it as if it did exist there. So 1 over -4 minus 4 is -4.25. Now this is going to be an open circle on that graph. So I'm going to circle that x value or that y value. At that point, that's our cutoff x value. So now I'm going to bump over into this third column, 2 to the power of x. And where I'm starting is at -4. So recall from our definition here, for the 2 to the power of x, it's x is greater than or equal. So this one is actually on the graph. 2 to the power of -4. Recall the negative exponent flips over the base. So that's 1 over 2 to the power of 4. Which is 1 to the 4th power over 2 to the 4th power, which is 1 over 2 times 2 is 4, times 2 is 8, times 2 is 16. 1 over 16, so very close to the x-axis there. Next value, 2 to the power of -1/3, is 1/2 to the power of 3, which is 1 over 8. 2 to the power of -2 is, again, the negative exponent flips over the base, so 1 over 2 to the power of +2. Half times half is 1 over 4. 2 to the power of -1 is 1 over 2 to the power of 1, which is half. 2 to the power of 0, that's one of my favorite things to simplify. It's so easy. It's always 1. Anything to the power of 0 is 1. And then 2 to the power of 1 is 2. So that's ready to graph. I'm going to start graphing this left-hand part of the piecewise function in red. So at -6 we're at negative 4.16, so very close to negative 4. At negative 5, we're at negative 4.2. And then at negative 4, I'm going to put an open circle here. That's negative 4.25. Again, it's not part of this graph, so as I sketch in this left-hand side, I see that it's kind of an asymptote at there at negative 4. It terminates there right at this open circle at negative 4, comma negative 4.25. That's where the other function picks up. So we'll start there. So it's right at 1/16. That's very close to 0. 1/8 is also close to 0 at negative 3. At negative 2, it's a quarter. Negative 1's a half. So this is that exponential growth function. As it goes, it gets very large. And I can start to predict values. 2 is squared is 4. 3 squared is 9, and so forth. So that right-hand side shows the exponential growth very clearly. So we've done that first task. We've graphed the function by creating the table of coordinate points. What we need to do now is determine what's happening to the function value as I get close to the discontinuity. What kind of discontinuity do we see here at negative 4? Is that a jump, an infinite, or a removable discontinuity? Good, it's a jump discontinuity. Both sides of the limit come to finite values, but they're not equal. So the way we're going to record the behavior, here's how we'll do the left-hand behavior. What we're saying is as I come from the left towards this value of negative 4, that's where the discontinuity is, what's happening to the y value? So as x approaches negative 4, and the way we say we're coming from the left is by putting this negative 1 up in the power. Really, it's not even a 1, it's just the negative symbol. So as x approaches negative 4 from the left, y approaches, and that's that number we had circled here. Really, we're saying that that y value, it's not on that graph, but y gets very close to negative 4.25. Okay, so that's for the behavior as we come from the left. As we come to negative 4 from the right, we're up there on that green function. So notice all the right values from negative 4, so negative 3, negative 2, those are in the range of this green function. So as x approaches negative 4, how do you think we notate from the right? Good, it's a little plus in the exponent. Y approaches, and here we actually have a value. It doesn't even approach, it actually equals 1/16. And that truly completes our analysis of the behavior of the graph around the discontinuity. Okay. Let's take a look at one more example. Our second example is a rational function. So we're looking at f of x equals negative 1 divided by x plus 2. So we'll start again with a table. That's the way we're going to begin all of these because we want to look at the graph. And f of x. And I'm just thinking in terms of the vertical asymptote, just doing a little initial analysis. That vertical asymptote's whenever I set the denominator equal to 0. And really what I'm saying is that denominator can never equal 0. So if I were to solve that, I'd subtract both sides. And what I would see is that x cannot equal negative 2. The reason I start there is that's going to be my middle value for x. So I'm going to center everything around negative 2. So negative 3 and negative 4. We'll back up to the left 2. Same to the right, negative 1 and 0. Now I want to calculate the output. So we're going to take that function f at -4, and all I'm doing is I'm substituting -4 for any x value. So it's over -4 plus 2. So this becomes, if I put that negative on the numerator 1, -1 over -4 plus 2 is -2. That's positive half, or 0.5. F at -3 is -1 over, again, I'm putting -3 where there was x, so -3 plus 2 in denominator, and that simplifies to -1 over -3 plus 2 is -1, or just 1. So -2, we've already seen, is going to be undefined. We can just demonstrate it here. F at -2 is -1 over -2 plus 2, which is -1 over -2 plus 2 is 0. Can't divide by 0. That's undefined. And the way we'll see that on the graph, recall, is as a vertical asymptote going through that x value. So we'll just go ahead and plot that. Okay, f at -1. Again, to write it there is to substitute -1 for x, so -1 plus 2 in denominator is -1 over -1 plus 2 is +1, so that's -1. And you can see that odd symmetry forming. Same number, different sign. F at 0 is -1 over, substitute 0 for x, plus 2 is -1 over 0 plus 2 is 2, so that's -half. And again, that odd symmetry, it's both 0.5s, but the signs are opposite. Let's graph those points. So at -4, we're at -0.5. -3, we're at -1. So this left side observes the vertical asymptote and the horizontal asymptote there at the x-axis. On the right side, we've got, oh, well, I plotted that entirely wrong. Let's fix that error. Can you see what I did wrong? It's -4 positive 0.5. Let's fix that. And then -3 positive 1. So that's going to definitely change our behavior of the function around the discontinuity. Ooh, good save. Let's catch that lower part then. So that's -1, -1, 0, -0.5. So this right side's down here in quadrants 3 and 4. So that, again, completes the first task, which is just to graph the function using a table of values. So we're going to say again what's happening to the value of the function, the y value, as we approach the discontinuity from the left. Before we say that, what kind of discontinuity do we have here? Our first example had jump discontinuity, which are functions coming up and equaling values, but they don't equal each other. Here I have one side that's going up an asymptote, the other that's coming from the roots of the asymptote. What kind of discontinuity is this? Is it jump? Is it infinite? Is it removable? Good, it's infinite. Remember, infinite discontinuity is when one or both of the sides around the discontinuity approach positive infinity or negative infinity, again, which can't equal each other. You can't set infinity equal to anything. Well, we got an infinite discontinuity. I didn't spell that right. Let me erase discontinuity, disco. Discontinuity. Ah, made it. Okay, as x approaches, so where was our cutoff? We found that at the very beginning. It was that place where we saw the discontinuity undefined. So as x approaches -2 from the left, So again, to say from the left, put that power negative. Y approaches, so the question is, where is this Y value headed to? It's increasing without bound. It's headed to positive infinity. Let's check the other side. So the other side is from the right. I'm gonna, again, I draw the arrows saying this is where I'm looking. From the right-hand side, I'm saying what's happening to that Y value as X gets closer to -2. So we're gonna write X gets closer, approaches -2 from the right-hand side. What's happening to Y? So I'm gonna look down here. Where is the function headed in terms of its Y value? Well, it's going down, 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 right? Forever. So what I'll say is X, as X approaches -2 from the right, Y approaches -infinity. And that really concludes our response to that second example. So we've seen one example that had a jump discontinuity. We've seen one that had an infinite discontinuity. Let's take a look at our last example. So here we've got another rational function that has more stuff, more parts, x squared plus x minus 2 over -2x squared plus 8x minus 6. If you recall from Algebra 2, when we go to graph a rational function like this, our first task is really to factor the quadratic above and the quadratic below. So what I'm going to do is rewrite this right in place. So just to the right of the original. I want to factor the numerator and the denominator. So for the numerator, keep in mind what we're looking for. I'm going to put coefficients of 1 for the A and the B, is what multiplies to the C term -2, but adds up to the B term +1. So what two numbers would multiply to -2 but add to +1? Multiply to -2, add to 1. Excellent. So 2 times -1 is -2. 2 plus -1 is 1. So this numerator would factor as x plus 2 times x minus 1. Let's do the same for the denominator. Before we do all that, I see that I have a 2, really a -2 is divisible out of each of the terms. 2, 8, and 6 are all divisible by 2. So I'm going to factor out, in fact, -2. And what that leaves us is x squared plus, I'm factoring out negative, so this is going to switch all the signs. So minus 4x plus 3. So then I'm going to work on that one in dark blue for the factoring. What multiplies to +3 and adds up to -4? Two numbers that multiply to +3, add to -4. Multiply to 3, add to -4. That's -3 times -1. -3 times -1 is 3. -3 plus -1 is -4. So let's write those. That's x minus 3 times x minus 1. Now, the reason we do this is to note any cancellations. Do you notice anything the same above and below? Excellent. So if you see this x minus 1 in both the numerator and the denominator, we can cancel it. Now I need to find the discontinuity. So the way I'm going to do that is set that factor and say that it cannot equal 0. It's a factor in the denominator. I can't have it equaling 0. So I'm going to add 1 to both sides. And what I see is that there's a discontinuity at +1. So I'm just going to mark here. That's +1. Whatever the y value is on the function itself, there's a gap or a hole there. Okay, so we're ready to graph some stuff. And let's create our table of values. Once you find that canceled factor, one thing that you can do, like we did on our previous one, is take the other factor that did not cancel, and let's find the vertical asymptote. So there we're going to say x minus 3 cannot equal 0. I'm going to add 1 to both sides, add 3 to both sides, and that will give me x cannot equal 3. So I'm going to locate that. That's our discontinuity. We got 2 of them here, guys. So put 3 in the middle, 4, 5, and 6. Now I do want to back up to at least positive 1. So 2, 1, and then let's go to 0 as well. Now there's a lot to record here. And so what I'm going to do, instead of doing all the arithmetic, I do want to just demonstrate one of our skills in pre-calculus is select the tool for the most efficient completion of the task. This is a bigger function. I think it's a good chance to use the Desmos calculator. So I'm going to head over, let me share that screen with you. And once we reach Desmos, I'm going to just type f of x. I'm going back to the original, equals, I hit divide to give the fraction. So in the numerator is x squared plus x minus 2 over negative 2x squared plus 8x minus 6. And that's good. I'm going to hit the home key over here. If ever you've gotten kind of on a different Zoom, you can hit the home key. And here's our graph. So we got a vertical asymptote we saw at 3. So let me just put in that x equals 3. And that looks good on the graph. But what I really want is a table. So I'm going to go up to that edit list, the cog, and then I'm going to say convert that to a table, please. And I don't really want negative 2 or negative 1. I'm going to keep going with 3. And 4 and 5. So we'll go to 5. So those are the output values for that function. So on the left-hand side, we got 0 is 1/3, 0.3 repeating. 1 is undefined. That's what we saw with the cancellation. Recall that? And on the graph, note there's kind of a limitation on the graphing calculator. At x is 1, it's actually showing a perfectly smooth connected curve. We know that there's a discontinuity at 1 though. So notice it's marked undefined, undefined. Now we'll be able to find what that value is from our canceled version, but right now in this function, it's not defined, even though the graph makes it look that way. The function climbs at 2, it's at 2. 3 is that vertical asymptote. So again, we got to say what's the function behavior there. And then we bump over into quadrant 4. At 4, it's at negative 3, 5 is at negative 1.75. Well, that gives us some good insight. I've recorded that table. Let's head over and finalize that on our note screen. So we'll finish this graph here. So at 0, what we saw was that was positive 1/3. So an output of 0.3 repeating. 1 was undefined. Now, what I need to do here, because what we're going to have to do in a moment is say, what's the behavior of the function as it gets close to 1? I'm going to use, let me outline it here in green, the parts of the function that I did not cancel. And I'm going to plug in 1 there. So to find the value of the function as it gets close to that undefined one, I'm just going to plug in 1 wherever x is. So 1 plus 2 over negative 2 times parentheses 1 minus 3. So in my numerator, I would have 3 over, that's negative 2 outside. It's also negative 2 inside. 1 minus 3 is negative 2. So negative 2 times negative 2 is positive 4. So the function has a value of 0.75 if I didn't have that discontinuity from the cancellation there. So we'll just hold on to that. We'll use it in a moment. We'll continue here. So at 2, it's at positive 2. 3 is our vertical asymptote. 4 bumps down. 4 is down at negative 3. Oh, and I didn't get all these for 5 and 6, so let's grab real quick. So 5's negative 1.75. And I'll just quickly take a look. In fact, we'll go there just to say, what do you do if you don't have enough x values, y values? You go there and click enter. Good, so negative 1.3 repeating. Easy to do. And let's graph it. So at 0, we're at just a third. At 1, we know that it's not there. So I'm going to put an open circle at 0.75. 2 is 2. And then 3 is the vertical asymptote. And remember how we found that? That was setting equals the denominator to 0. What didn't cancel, that x minus 3, and solving. So that left side, it looked like it kind of went down. We don't really know what that horizontal asymptote is, but at this point, we don't need to know. I just know it went below the y-axis. I'm going to guess it's at about negative 1/2. All right, on the right side, we're at 4, negative 3. We're at 5, negative 1.75. And at 6, we're at negative 1.3. Trace that up. And there's our graph. So we've graphed that function. How many discontinuities are there? How many do you see? Well, the one at positive 1 is a jump discontinuity. We're just going to write jump disco. That's right. So let's work on the jump discontinuity first. So we'll consider from the left-hand side. So as x approaches, and you always take that x value, so it's 1 from the left. Y approaches what value? Now, we calculated it. And we used the version that didn't include the x minus 1s that we canceled. So when we calculated it, it's at 0.75. Okay, let's calculate also from the right-hand side. So that's approaching positive 1 from the right. So we'll write that as x approaches positive 1 from the right-hand side, y approaches also 0.75. Good. Notice they're approaching the same y value. And that, remember, that's the way we defined a jump discontinuity. Good. Okay, so our second discontinuity here is at positive 3. And that one was when I set the denominator equal to 0 on the part that didn't cancel. So what kind of discontinuity is that when we have a vertical asymptote? Is it a jump discontinuity? Is it an infinite discontinuity? Or is it a removable discontinuity? Excellent. It's infinite. Infinite discontinuity. Now, I've made a mistake here. Can you see my mistake? I called this a jump discontinuity. Is it a jump discontinuity when my y values are equaling each other, even though the function itself doesn't have a defined value at that point? No, Muchler. No, it's a removable. So I named it incorrectly. Let me correct the error. Removable. The error is removable. Okay, so let me catch back up. So I've fixed that error. Let me know if you catch any others. So let's talk about this discontinuity at +3. So now I'm considering what happens to the y value as we approach 3 from the left. As x approaches 3 from the left-hand side, y approaches. So I'm going to look at the top of this left-hand graph. Where's it headed? Where is y going? Excellent. It's going to infinity. It's headed into the heavens. Last part here, where is y headed as we approach 3 from the right-hand side? So as x approaches 3 from the right, y approaches. So again, we look at the graph on that lower part of the graph. Where is that y value headed? It's descending down, 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 negative infinity. And that completes the behavior of this rational function around its two discontinuities. Thanks for joining. I'm going to let you work on some of your questions. Until next time, bye-bye.